Section 8.5 continued. In this part of the section, we'll discuss how to solve logarithmic equations. To help us do that, we need the change of base formula. The change of base formula helps us determine the value of logs with any given base. For any positive numbers m, b, and c, with b not equal to 0 and c not equal to 0, we have log base b of m equal to log base c of m divided by log base c of b. In our determination of this value, we're going to use a calculator, and we're going to use the common log of m divided by the common log of b. In our first example, use the change of base formula to evaluate each expression, then convert to a logarithm in base 6. We have log base b of 7. I'm going to use the change of base formula to find out the value of this log. Therefore, I'm going to have the common log of 7 divided by the common log of 3. And now I can plug that into my calculator to get that value. I just have the log of 7 divided by the log of 3. And that gives me a value of, when I round to the nearest 10 thousandths, 1.7712. Now I want to convert this to a value in log base 6. So I have log base 3 of 7. I want to convert that to log base 6 of a value that I need to determine. Now we know how to solve these because we can change this value into 1.7712. That's its approximation. 1.7712 equals a log 6 of x. And again, we can solve this because we know how to change this into an exponential function. That gives me x approximate to 6 to the 1.7712 power. Now I can just plug that into my calculator and get an approximation for my value for x, which will be in base 6. Therefore, 6 to the 1.7712 exponent, and I get a value for x that approximates to 23.8925. In this example, again, I want to use the change of base formula to evaluate each expression, then convert to a logarithm in base 6. Again, I can use the change of base formula, which will give me the log, or common log, of 0.125 divided by the common log of 20. I can substitute this value into the calculator. Log 0.125 divided by the log of 20. And that will give me a value of approximately negative 0.6941. Now I want to convert that approximation into a log of base 6. So I have log base 20 of 0.125, and I want to convert that into a log of base 6. I want to find the value of x. But I know what this approximation is. We found that to be a negative 0.6941. And then I can convert that into an exponential form. X will approximate to be 6 to the negative 0.6941. Then I can plug that into a calculator and get an approximation for x. 6 to the negative 0.6941. And I get x to approximate to 0.2883. In my next example, I want to solve each equation. I also want to make sure I check my solutions. Here I'm given the common log of 3z equals 2. I want to write this as an exponential equation. I know the common log has a base of 10. Therefore, I have 3z equals 10 to the second. Now I can simplify this, and I'm going to have 3z equals 100. Divide both sides by 3, and I get z equal to 33 1/3. Now what I can do is use my calculator and substitute z into my original equation. And that's going to give me the log of 3 times 33 1/3. And when I do that, I will get a value of 2. Therefore, that is the correct solution. On my next example, I have the common log of the quantity 2x minus 4 equals 3. Again, I want to write this as an exponential equation. I have 2x minus 4 equals 10 to the third. That gives me 2x minus 4 equals 1,000. Add 4 to both sides, and I'm going to get 2x equal to 1,004. Divide by 2, x equals 502. Now, what I'm going to do is substitute that value back into a calculator. And when I do, it's going to look like this. Log 2 times 502 minus 4. And when I do that, I will get a value of 3. Therefore, I know this is the correct solution. In my next example, I have the common log of 5x plus the common log of the quantity x minus 1 equals 2. I need to use the properties of logarithms to simplify the left side. I'm going to use the product property. That will give me log of 5x times x minus 1 equals 2. I knew it was the product property because of the plus sign. Now what I need to do is write this in exponential form. That gives me 5x minus x minus 1 equals 10 squared. Let's simplify both sides. That gives me 5x squared minus 5x when I distribute, and that equals 100. I'm going to set this equation to 0, which gives me 5x squared minus 5x minus 100 equals 0. I'm going to factor out a 5. That gives me x squared minus x minus 20 equals 0. Now, bring down my 5 and factor again. But this time into 2 sets of parentheses. Give me x, and I know this minus sign tells me I'm going to need 2 values that multiply to give me 20, one positive, one negative, and the 2 numbers will have to subtract to give me this negative 1. That will be a minus 5 and a plus 4. And you can FOIL that to show that that actually works. Now I solve. 5, of course, can't equal 0. X minus 5 set to 0 gives me x equal to 5. And x plus 4 equals 0 means x equals a negative 4. Now I'm going to substitute these values, 5 and negative 4, into my original equation. And when I do, 5 will work out, and that will look like the log of 5 times 5 is 25, plus the log of 5 minus 1 is 4. Using my calculator, I'm going to get a value of 2. Therefore, it works. When I substitute in a negative 4, I'm going to get an error. Therefore, this won't work. In this example, I have 2 times the common log of x minus the common log of 8 plus the common log of 1.2 equals 3. To simplify the left side, I'm going to have to use the properties of logarithms. The first term, I'm going to use the power rule, which is going to give me the log of x squared minus the common log of 8 plus the common log of 1.2 equals 3. Now I can use the quotient rule, That will give me the common log of x squared over 8 plus the common log of 1.2 equals 3. Then I can use the product property. So I'm going to multiply 1.2 times x squared over 8, which will give me the common log of 1.2 x squared over 8 equals 3. I could have done that in quicker steps, but I wanted to show you every step along the way. Now I'm going to change this to exponential form. Since the common log has a base of 10, that will give me 1.2 x squared over 8 equals 10 cubed. Simplifying the right side, I get 1.2 x squared over 8 equals 1,000. Multiply both sides by 8 gives me 1.2 x squared equals 8,000. Divide both sides by 1.2, I get x squared equals 6,666 and 2/3. Take the square root of both sides, and I'm going to get x equal to be plus or minus 81.6497. Now I'm going to substitute those values back into the original equation, which is 2 common log of 81.6497 minus log 8 plus log of 1.2. And when I calculate that, I'm going to get an approximation of 3. Therefore, I know that positive 81.6497 is going to work, while when I do the same thing with a negative 81.6497, I get an error. Therefore, the approximation for x is 81.6497. My next example, I want to solve the equation 2 times the common log of x minus 2 equals 3. I'm going to show you 2 different ways to solve this equation. The first one, I have 2 times the common log. Therefore, what I'm going to do is divide both sides by 2. That will give me the common log of the quantity of x minus 2 equals 3 divided by 2. I can do that on this equation because I don't have any other terms on the left side. While on my previous example, I have a 2 here, but if I would have divided by 2 on both sides, I would have to divide this by 2 and this by 2. And they aren't going to be in logs, so that would cause more difficulty. So here, since there's no other terms on the left side, I can divide both sides by 2, and the 2 cancels, leaving me just the common log of x minus 2 equals 3/2. Now I want to write this in exponential form. That gives me x minus 2 equals 10 to the 3/2 power. And I'll simplify the right-hand side, and using my calculator, I get 10 to the 3/2 to be 31.6228. Now I'm going to add 2 on both sides, and x will equal 33.6228. Now when I substitute that back into the original equation to verify, it will work. So when I substitute in the calculator, it's going to be 2 log of 33.6228 minus 2. And when I calculate that, I do get an approximation to 3. Therefore, I do know that this is a solution to my problem. But as stated before, I have a different way of solving this problem. I can use the properties of logarithms. Here, the power rule, which would give me the log of x minus 2 squared equals 3. Now, changing that to exponential form gives me x minus 2 squared equals 10 to the 3rd power. Simplifying both sides, I can get x minus 2 times x minus 2 equals 1,000. Foiling, I get x squared minus 4x plus 4 equals 1,000. And when I set to 0, that gives me x squared minus 4x. Subtract 1,000 on both sides, I get 996. So what I'd like to do is factor this, but it won't factor. Therefore, I have to use a quadratic formula. When I do that, that's going to give me 4 plus or minus the square root of 16 plus 3,984 over 2, which essentially breaks it down into x equals 33.6228 and x equals a negative 29.6228. But we've already substituted in this value, so we know that that is a solution, as we've seen over here. But when I substitute this back into the equation, the negative 29.6228 won't work. Therefore, I still end up with the same solution, but this is a lot quicker.